Welcome all my dear students. Today is a lecture 4 of CS 302 Data Structures. I'm Dr. Sangeeta Bhattacharya. Today we are going to start with the first data structure of our course, and that is array. And in this lecture we are going to learn about the different representations of array in the computer memory, namely row major and column major. First, a brief recapitulation of what array is. So as I know, array is a collection of similar data items. What does that mean? So here we can declare something like this. So if we declare something like int a5, so a is a single dimension array which will be containing elements of integer type. So this is what means by this statement. So instead of int, it can be float, this can be char, and so on. Now, so if I write int a5, that means a is the name of the array which is having a size of 5 and it will be containing 5 integer elements. Instead of 5, if I write 10, that means it will be a is an integer array which will be containing a maximum of 10 elements and so on. The first property of array is that the elements of this particular array, suppose A5, 1, 2, 3, 4, 5, will be stored in continuous memory location. So if I draw a memory map like this, so 1, 2, 3, 4, 5. So this is 1, this is 2, this is 3, this is 4, and this is 5. And the memory locations will be something like, if it starts from 200, it will be 204, it will be 208, assuming it's a 64-bit compiler and it's a 4 bytes is the size of integer. It is 212 and this is 216. So if I know the base address of this array, that is, if I know the address of the first element of this array, I can find out the memory address of the nth element of this array. So this is the property of array. If we can find out the address of the first element, we can using that address we can find out the address of any element in the array, and that will be typically something like this. So if the starting address or the base address of the array is considered to be BA, then the address of, suppose, a nth element can be found out by base address plus the size of the data type into n. So using this concept, if I want to find out the address of A2 in this example, it will be the base address is 200 plus size of the data type, means this array is of integer type, so the size is 4, into what is the value of n? The value of n is 2. So it is 208, and from this diagram we can see that indeed the address of A2 is 200. So this is the property of array. Next, if I want to access the elements of this particular array, I have to use the concept of index of subscript. So what is it? So this array, again I am drawing it. So this is the element A0. This is A1. So consecutive memory locations means this, that the elements of the array will be stored one after the other with no gapping or overlapping. And dot, dot, dot. So this one is known as the index of the element or subscript. So each element of the array can be accessed via this indices or the subscript. The fourth important point is it is a derived data type. Now, why it is a derived data type? Because if if we look at this example, in this example, int A5, there is nothing called array data type in any programming language. To define an array, we have to make use of the primitive data types or primitive data structure, which are int, float, char, boolean, and so on. So whenever some data type is made out of the primitive data types, we call that type of data types derived data type. Therefore, array is a derived data type. And the last important point is it's a linear data structure. Now here there are two terms. The first one is the data structure. Why we are calling array as a data structure? Let us look at this. So when I told you what is a data structure, I told there are two important properties of a data structure. The first one is how it will be stored in memory, how it is stored in memory. It means here the data is stored in memory. So let me write the data, how the data is stored in memory. So this is one property. And the other property is operations allowed. So if I talk about this, then array is having both these properties. So in the memory, it is stored in form of continuous memory location. So, and the operations which are allowed on array are typically, it can be many. So one, it can be insert, so we can add elements to this array. Two, we can delete elements from this array. We can delete any element. Third one is access. We can access any of these elements. Then fourth one is we can search for any elements in this array. Then fifth one, we can sort any elements and so on. So there's a different kind of operations which can be performed on this array. So that's why it is known as a data structure. And why it is known as a linear data structure. The second important point is the linear data structure. Now, for the linear data structure, it means that the elements has to be accessed in a sequential manner. So if we want to access the element 4, that is if we want to access the third element of this array, we have to go sequentially starting from the index A0. So first we will be accessing the element A0, then we have to go to A1, then we have to go to A2, and like this, we have to go reach AN. So without traversing A0, we cannot traverse AN. So this is why it is known as a linear data structure, because here the access method is done in a sequential manner. That is one after the. So these are some basic properties of array data structure. So now I'll move to the dimension and the representation of an array. Now let us see this example. Here, array can be considered to be of multi-dimension. So here, it is a single dimension or one dimension and the most popular data structure which is used. So suppose I have written A5 and the elements are 10, 20, 30, 40 and 50. In the memory, how it is going to be stored? So sequential 10, 20, 30, 40, 50. And the memory mapping will be something like this. So again, the assumption it's of 4 bytes. So 2000, 2004. So these are the memory addresses. So these are the memory addresses. Now, if we talk about the two-dimensional array, then the two-dimensional arrays. So in case of two-dimensional array, we usually represent the array like this. So it's A, 2, 3. So it's a two dimension. One is the row and the other is the column. And 10, 20, 30. So we can also write it in this way, or we can also write it in this manner. So A, 2, 3. and we can write it like 10, 20, 30, 40, 50, 60. We can also do it in this manner. But what is to be observed is that this is a two-dimensional array, and whenever we mention the dimension, the compiler will arrange it in the memory accordingly. So the representation is like this: 10, 20, 30, 40, 50, 60, and the memory representation is like this. Now here one thing you observe that here I have separated it into two parts. So this is one part and this is one part. And if you remember in C, we have learned that whenever we are representing two-dimensional arrays like this, then it is basically considered to be multiple one-dimensional arrays. So in this case, the row number represents, the number of one-dimensional arrays, and the column number represents the number of elements in each one-dimensional array. So in this case, because we are having A, 2, 3, so number of rows is 2, that means there are two one-dimensional arrays, and the number of elements in each one-dimensional array is 3. So this is 10, 20, 30, and this is 40, 50, 60. But again, you observe one thing, students, that the representation of memory is sequential. So even though whatever is the representation one-dimensional like this, the elements are arranged in a sequential manner. So this is a two-dimensional array. Like this, we can exchange this kind of notions to multi-dimension. So let us now go to the memory representation. So we have learned about C because we have studied C programming language. So we are seeing that the elements are arranged like this. So what is this actually called? So there are array representations in memory. There are two types. The first one is a row major. What is row major? See, in the row major representation, the rows are stored one after the other in the linear memory. How? So, if this is a two-dimensional array, so it's 10, 20, 30, 40, 50, 60. So this is 10, 20, 30, 40, 50, 60, and this will be stored in a sequential manner. And if we have to calculate the linear offset from the beginning of the array to any given element, then we have to use this formula. So the formula is R. That is, if we want to find out, let us see this example, A02. We want to find out the offset. What is the offset? Offset is from the beginning. So this is the beginning of the array to the particular element. So what we want to find out the offset for A02. So how far, in other meaning, how far it is from the beginning of the array. So offset can also be defined like this. How far is an element from the beginning of the array? So how far it is from the beginning of the array. So offset can also be defined like this. So let us see. So if I'm talking about the element A02, how far is it from the beginning of the array? So row, what is R? R is 0 here. So R is 0 into the number of columns. So 1, 2, 3, 3 columns we are having plus the column number, which is 2. So it's 0 into 3 plus 2, which is 2. So let us go back to this diagram and check. So this is A02. And how far it is from the beginning of the array? It is 2 elements apart. So 1 and 2. So this is called the offset. Similarly, we can find out the offset for some other elements. Let us consider this. So offset of A1. Let us find out offset of A22 will be equals to what? Row. Row is 2 into number of columns we are having in this array is 3. And what is the column number? 2. So what is it? It is 6 plus 2 is 8. Let us check. So it doesn't have, so, okay, so there is a mistake. So this doesn't have 8 elements. So let us do it for 1. So this will be 4. Now let us check how far it is from the beginning of the array. So this is A11. We can see here, this is A11. And let us check from the beginning of the array, how many elements, how far is that element from the beginning? So this is the beginning. So it is 1, 2, 3, 4. We see it is 4. So this is meant by the term offset. So now let us go back and go and check how this element is actually stored in the memory. See, so this is our given example. Let us see how it is stored in the memory. So in this example, you can see that in this case, so it is if we represent it normally, it will be represented like this, and because it's a row measure representation, what we told, the elements will be stored one after the row after another row. So this is the first row, 10, 20, 30. So 10, 20, 30 has been stored first, and 40, 50, 60 is the second row. So the 40, 50, 60 is stored in the other row. Now, for calculating the address of any given element in the array or any given index in the array, we can use two formulas. The first formula is using the offset. So, offset is how far is that element from the beginning of the array. So, we can use the formula base address, where base address is the starting address of the array. So, in this case, it is 2000 plus size of the each element of the array. So if in this case, if I am using int, so it is int. So this is very important. If it is float or it is char, then it will change. So this is int. And if it is double, it will change. So int. So this is very important. Int. So int A23. So what is the size? So that is W into offset. We can either use this formula, or we can also use this formula where if the indices are starting from 1 and I equals to 1 and j equals to 1, that is if the indices are starting from 1, then we have to use this formula dA plus W into m into I minus 1 plus j minus 1. If you see this part nicely, this is basically the formula of the offset. So what was the formula of the offset for the row measure? Let me just write it down once. So the formula for the offset was R, that is R means the number of columns, number of row. So whatever is a row given, so here my row is given I into the number of columns. So what is the number of columns? M plus the column. So that is here j. So if I am considering for Aij element, for the Aij element, the offset will be first the row, so that is I, into the number of columns. So number of columns is m plus the column. So that is j. So you see these two formulas are basically equivalent. So that is only expanded and written in this form. So what is this? This is I. If it is starting from I and j are starting from 1, then we use this formula. If it is starting from 0, we simply write I and j. So this is the formula for the offset. Right? Now let us see with the help of this example. So this is my elements, and internally it will be stored in this fashion, but if we want to write, we can store it in this fashion, 10, 20, 30. So the first row is written first, and then the second row, 40, 50, 60 is stored in this order. Now if we want to find out the address of A02, so what is A02? So the base address of this address, or the starting address of this array, is 2000 plus 4 is the, because it is of integer type and it is a 4 bytes we have assumed. So 4 into what is in the number of columns is 3. What is the row number? 0 plus 2 means the column number which is equals to 2008. So let us check A02. What is A02? A02 is 30. And let us check where it is stored. Yes, it is stored in 2008. So this is using this formula of expanded form, and this is using our normal offset form. Now, you see, we have not used a minus here. Why? Because here the indices have started from 0. If it has started from, instead of A00, we would have started from A11, then we would have done -1. So, if in exam you are given any problem on this finding out the address in row major or column major representation, you should be very careful about what is given, whether it is the indices of the array is starting from 0, 0 or it is starting from 1, 1. If it starts from 0, 0, simply use the row number and the column number. If it is starting from 1, 1, then we have to do a minus. So you should be very careful about that. So this is a row major representation where if you declare an array, the elements are stored in a row after row. Now, which programming language follows this row major representation? So we have done the C language. So in C, basically, in the programming language C, row major representation is followed, and therefore if you write any array like this in a C programming language, you will be seeing the addresses are given in this similar fashion. Now, what is the other representation? So this is a row major representation where the rows are stored one after the other in a linear memory, in linear fashion in memory. Now, if we go to the other representation, that is known as a column major representation. So it is just the reverse of the row major representation. So if suppose a two-dimensional array is like this, so if you declare an array like this in a column major representation language, then the elements will be stored in this fashion. So 10, 40, 20, 50, 30, 60. So this is my array, and this will be stored. You have to declare. So if you want the array to be like this, you have to declare in this fashion. So see the difference between the two. So in case of a column major, so in row major representation, it was like this. If you remember, so it was 8, 2, 3, and then we were simply 10, 20, 30, 40, 50, and 60. So this was the row major representation, in which the elements were declared in the same fashion. So A, 2, 3 is equals to 10, 20, 30, 40, 50, and 60. So it was in the same way how it is represented. But in case of a column major one, this has to be declared in this fashion. So this is the difference between the two. In case of row major, we are storing rows after rows. In case of column major, it is column after column. So if we have to calculate the linear offset from the beginning, so from the how far is an element from the beginning of the array, so it will just the reverse of the row major. So in case of row major, it was R into number of columns plus C. In case of column major, it will be C into number of rows plus R. So let us see the example of A02. So A02, how it will be stored? 10, 40, 20, 50, 30, 60. So if how far is A02 from in this array? So let us see. So from the beginning of the array, it is 1, 2, 3, and 4. And see, we are also getting 4 here. So A02 is far from 1, 2, 1, 2, 3, 4. And if we use it in the formula, so column is 2 into number of rows is 2 plus 0, which is 4. So you see, A02 is 4 elements apart from the beginning of the array in column major. if we talk about the row major representation, so if we talk about the row major representation, then in row major, this was what? So offset of A02 would have been row. So what is the row number? 0 into number of rows was 3 and column number was 2. So it was 2. So 0, 1, 2. So it is 2 elements apart. So this is the difference between the row major and the column major representation. Row major representation is followed in the common languages like C, C++, but the column major is followed in the languages of Fortran and MATLAB. So in this kind of programming languages, column major representation is followed. Now let us go and check what will be the formula for finding out the address of a particular element in this case. So in the column major representation, if we check, this formula remains the same. That is, here we are actually doing BA plus W into offset. Now, what is the offset here? So if you remember, the offset is, because we are doing in a column major representation, so the offset will be n into j minus 1 plus I minus 1. So it's just the reverse of the row major representation. So it's just the reverse of the row major representation. So in case of row major representation here, it was, so if you remember, the offset was, in case of row major, the offset was R into number of columns plus number plus the column number, that was J. In case of column major, it is just the reverse. So it is C, that is the column number into number of rows plus the row number. So R is the number of rows in the array. J minus 1, if the array indices are starting from 1, so it will be J minus into J minus 1 plus the row number, which is I minus 1 in case of I equals to 1 and J equals to 1, and I if it is 0, 0. So it's just the reverse. If you remember 1, you can use that logic for finding out the other also. Now, if we look at the representation, if we just go and look at this representation, what we see is that, so here, as I have told you, here the elements will be stored in this fashion. So 10, 40, 20, 50, 30, 60. So it will be stored in a column wise manner. So 10, 40, 20, 50, 30, 60. So it is stored in this fashion. Now this, what I have written here, see, the elements are stored in this fashion. 10, 20, 30, 40, 50, 60. Now, internally, so this is completely internal. What I have written here, it's not you declare it in this manner. You could have also declared it in a normal, usual fashion like this. 10, 20, 30, 40, 50, 60. And then it will be, the two-dimensional array will be like this. And then internally, the system will be doing it like this. So this is the first column. So the first column, second column, and the third column. If we look at the offset, now let us check using this formula. So the base address plus what is the size of the each element in the array, 4 into, then what is the row? Now offset, let us think of the offset. What is the offset? So offset is the column. So the column number is 2 into the number of rows, which is 2 plus 0, and then it is 2016. So see, A02 is stored here in, A02 is 30 and 30 is stored in 2016. While in case of row major, it would have been something like this. So this is in case of row major. It would have been something like this: 2000 plus 2000 plus 4 into, so I'm talking about the row major representation. So the row number is 0 into number of columns is 3 plus what is the column number? 2. So it would have been something like 2008. But in this case, it is 2016. So here it is 4 elements apart, and there it was 2 elements apart. So this is in the column major representation. So this declaration depends on the type of language you are using. So it's not necessary that we will be declaring it like that. We can also declare it in this fashion. Now, if we are talking about this array representation, then one more important thing comes into play, that how the pointer representation is there. So here I will be just making it like internally it may be stored like 10, 20, 30, 40, 50 and 60. So this will be what? Internally it will be converted into this. So you need not declare it explicitly like. Now, if I talk about something called the pointer representation of it, then in a row major representation, you can imagine it to be something like this. So this is the first row. The first row can be termed as B. So this is A. This is the A plus 1th element and row, and this is the A plus 2th row. And each of these columns, so suppose if it is A, so suppose my row is, array is A34, then each of these elements can be termed as, this is A0, 0, this is A01, and so on. And how can we write this in other terms? So we can write this element as star of A, this element as star of A plus 1, this element A02 can be termed as star of A plus 2, and this element can be A03 can be written as star of A plus 3. So in case of a two-dimensional, this is a row major representation. Remember, this is a row major representation. So I'm talking about the C language more specifically. So in this case, we can represent the elements like this. So the first row can be represented, as star of A. So this element. Second element in the first row can be represented as star of A plus A, and so on. So basically, star of B, star of A plus I will basically give me the ith row. So star of A plus I will basically give me the ith row. So we can call this, we can represent this array in this form also. So it can be written, declared as int of 4 or int of star 4. So it's basically a pointer to an array. So it's basically a pointer to an array. One more important thing which needs to be known here is that if suppose I am writing something like star of b plus I plus j, what does this mean? It means that we want to access, so this basically means that we want to access the jth element in the ith row. So it basically means this thing. So start of b plus I, so we know that b plus I, this represents this part. This part represents the ith row and this part represents the jth element in that ith row. And this is equivalent to writing ampersand b of ij. This is equivalent to writing b of ij. So we know that the two-dimensional arrays are generally accessed via two indices, I and j. So this is equivalent to writing like this. Now, if we want to access the element of bij, so let me write down here. Let me redraw the diagram of the array so that you can understand. So let us consider it's a two-dimensional array and each consists of 3 elements. So the previous example what we have done, so this is 10, this is 20 and this is 30 and this is part is 40, 50 and 60. So now if I consider this, so there are 2 rows. So this is basically, we will be writing like this, A of 2, 3. A of 2, 3 is this array. Now in this array, if I want to access a particular element using the pointer notation, so writing like this will give me the address of the jth element. So 30, if I want to have the address of 30, I will be writing for the element, suppose 30. So I can access the address of 30 via using writing like this, b of I. So what is the 30? So this is 0, 0, 0, 1, 0, 2. So I can write it like b of 0 plus j, which is 2. If I want to access, so this will give me the address of 30. If I want to access the element 30, then you know that we have to use the dereferencing operator, which is star. So star of b star of star b plus I plus j. So if I want to access the address of the element 30, I will be writing like this. If I want to access the element 30, I will be writing like star of b plus I. So here b will be replaced by 0 plus j and j will be replaced by 2. So this is going to give me the element 30. So in case of two-dimensional arrays, we can do it like this. And why I am telling is that this part is very important because in most of the cases, programs, if you're writing using data structures, in most of the cases, our implementation will be mainly based on pointers. We will be doing it with the help of pointers. So if you're doing it with the help of pointers, it will be easier for you. Now there are some equivalents. So I will just tell you the equivalent pointer notations. So the first one is star of, we have already seen this. So if I write star of b plus I plus j. This is basically equal to writing b of ij. So b, as I have told you from this part, so this is equivalent to writing b of ij. So if I write it like this, it is basically b of ij. So what is b of I here? B of I is 0 and j is 2. So I can either write it like this or I can use the pointer notations like this. The next part, so the next is, if I write star of b plus I plus j, I already told this is equivalent to writing ampersand of dij. That means I am accessing the address of the jth element in the ith row. Next, if I write star of bi plus j, then you can see this is equivalent to writing b of ij. Why? I will be just explaining you that. See, compare this notation with this notation. So here star of b plus I, if you see in the previous slide what I have explained, star of b plus I is basically equal to bi. So this means we are accessing the ith row. This means we are accessing the ith row. So we can always replace star of b plus I with bi, and then it is equivalent to this, where star of b plus I is getting replaced with bi plus j, means we are trying to access the b plus I jth element. Next, b of I plus j, you can see that this is equivalent to writing ampersand of bij. Why? Because again, if we go back here, star of, so let us go back to this point. So let us compare this one with this one. So see, star of b plus I means bi plus j means, so this means we are trying to access the address of the jth element in the ith row. And at the last, we can also write it like this. So these are all things which needs to be understood. So you can just write your own program and you can just check this out so that it will be clear to you that why these notations we are using. So we can also write like this, b of b plus I. So this will give me the address of star of b plus I will give me the address of the ith row. If I want to write like this is equivalent to writing b of ij. So again, it's very simple because you see star of b plus I is this part. So this we can write as bi. And then if we write the index, so this is the combination of pointer and index. So if we write the index, this part is equivalent to this part and j is this. So this is equivalent to writing b of ij. So you can form your own notations like this if you understand the logic very clearly. I hope that this today's lecture will be helpful to you to formulate this kind of things, this kind of pointer notations from arrays. And remember, again, I'm telling this is very important because in most of the implementations, we will be using this kind of array and pointer. Thank you very much. In the next lecture, we are going to see about one more linear data structure and a popular data structure, which is known as linked list. Thank you.